Dear students, in last class we designed a low-pass FIR filter using Fourier transform. Today we will look into some of the window functions and then design FIR filters using window functions. Types of windows. First one is rectangular window. The n-point rectangular window WR of n is defined as rectangular window WR of n equal to 1 for n value varying from minus of n minus 1 by 2 to plus n minus 1 by 2 equal to 0 otherwise. Second type of window is Bartlett or triangular window. Triangular window is denoted by WT of n and is defined as 1 minus 2 into absolute of n by capital N minus 1. N varying from minus of n minus 1 by 2 to plus n minus 1 by 2 and is equal to 0 otherwise. The third window is Hanning window denoted by WC of n and is equal to 0.5 plus 0.5 into cos of 2 pi n upon n minus 1 for n varying from minus of n minus 1 by 2 to plus of n minus 1 by 2 and is equal to 0 otherwise. Fourth window is Hamming window. Hamming window is denoted by WH of n and is given by 0.54 plus 0.46 into cos of 2 pi n upon n minus 1 for n equal to minus of capital N minus 1 by 2 to plus n minus 1 by 2 and is equal to 0 otherwise. Next window is Blackman window. Blackman window is denoted by WB of n and is given by 0.42 plus 0.5 into cos of 2 pi n upon n minus 1 plus 0.08 into cos of 4 pi n upon n minus 1 for n equal to minus of n minus 1 by 2 to plus of n minus 1 by 2 and is equal to 0 otherwise. Next window is Kaiser window. Next window is Kaiser window. Kaiser window is denoted by WK of n and that is equal to I naught of beta 1 divided by I naught of A for n equal to minus of n minus 1 by 2 to plus of n minus 1 by 2 and is equal to 0 otherwise, where this beta 1 is given by A into 1 minus 2n upon n minus 1 squared whole raised to 0.5 and A is independent variable that can be varied to control the side lobe levels with respect to the main lobe peak. The modified Bessel function of I naught of x is given by I naught of x equal to 1 plus summation of 0.5 x square whole raised to k upon k factorial squared from k equal to 1 to infinity. So while calculating I naught of beta 1, we will have to substitute for beta 1 in place of x. Next we will see designing of FIR filters using window functions. First step, like in case of designing FIR filter using Fourier transform, here also for desired frequency response HD of e raised to j omega, we have to determine HD of n using Fourier inverse transform. And then in step 2, we have to calculate n minus 1 by 2, and for minus of n minus 1 by 2 to plus of n minus 1 by 2, we have to compute window function sequence and HD of n. Instead of calculating window function sequence for n value varying from minus of n minus 1 by 2 to plus of n minus 1 by 2, we can also calculate window sequence from n equal to 0 to n minus 1, that is small n equal to 0 to capital N minus 1. In third step, we have to multiply window function sequence and HD of n to get h of n. In fourth step, we have to find h of z by taking z transform of h of n, and to make h of z a causal systems transfer function, we have to multiply it by z raised to minus of n minus 1 by 2. If in last step we have calculated h of n for small n equal to 0 to capital N minus 1, then here we need not multiply z transform by z raised to minus of n minus 1 by 2, and the limits for summation are to be taken for small n equal to 0 to capital N minus 1. In last step, that is fifth step, we have to go for verification of the design of a FIR filter by plotting frequency response graph. Now we will take one problem based on designing of a FIR filter using rectangular window. Design a linear phase FIR low pass filter using rectangular window by taking 7 samples of window sequence and with a cutoff frequency omega c is equal to 0.2 pi radian per sample. So here in this question we have to make use of rectangular window of length 7 samples, and the cutoff frequency is given as 0.2 pi. Solution. Given h of e raised to j omega equal to e raised to minus j alpha omega. Remember, in designing FIR filters using window techniques, the bandwidth will be given. The filter type may be any one. It may be low pass filter, high pass filter, band pass filter, or band rejection filter. We have to take the frequency response h of e raised to j omega as e raised to minus j alpha omega, whose magnitude is 1 here. The coefficient of e raised to minus j alpha omega is 1. That is its magnitude. For omega greater than or equal to minus omega c and less than or equal to plus omega c and is equal to 0 for other frequencies. So we'll write here otherwise. Can call it as HD here. So right here now. To compute impulse response HD of n let us take inverse Fourier transform of HD of e raised to j omega. That is desired impulse response HD of n is equal to 1 by 2 pi integration from minus omega c to plus omega c e raised to minus j alpha omega into e raised to j omega n d omega. Integrating, we get 1 by 2 pi e raised to plus j omega into the bracket n minus alpha upon j into the bracket n minus alpha with the limits minus omega c to plus omega c. Substituting for upper and lower limits in place of omega, we get 1 by 2 pi into the bracket e raised to j omega c into n minus alpha minus e raised to minus j omega c into the bracket n minus alpha whole divided by j into n minus alpha. Now taking this 2 inside the bracket, we get 2j here. Then e raised to j omega c into n minus alpha minus e raised to minus j omega c into n minus alpha upon 2j will become sine of omega c n minus alpha. So you can write this as sine of omega c into bracket n minus alpha by n minus alpha, or we can rewrite it as hd of n equal to sine of omega c into the bracket n minus alpha whole divided by pi into the bracket n minus alpha for all n except n equal to alpha, because if n becomes equal to alpha here, hd of n will become infinity. Where alpha is equal to n minus 1 by 2, that is 7 minus 1 by 2 equal to 3. So I have to get now hd of n for n equal to alpha, that is small n equal to 3. hd of 3 equal to, for finding hd of 3, what we have to do? We have to go to the initial step, that is 1 by 2 pi integration from minus omega c to plus omega c e raised to minus j alpha omega into e raised to j omega n into d omega. So 1 by 2 pi minus omega c to plus omega c. If we multiply these two, we get e raised to j omega into the bracket n minus alpha d omega. And if I substitute for n equal to alpha, this exponent value will become equal to 1 at n equal to alpha. One by 2 pi minus omega c to plus omega c e raised to 0 d omega we get, and e raised to 0 is 1. So 1 by 2 pi integration of 1 with respect to d omega is omega only. So omega with limits of minus omega c to plus omega c, that is equal to 1 by 2 pi omega c minus of minus omega c So this we get as 1 by 2 pi into 2 omega c. 2 and 2 will cancel. HD of 3 will become omega c by pi. And omega c is equal to 0.2 pi. Therefore, 0.2 pi upon pi simplifies to 0.2. Now we will evaluate HD of n for n values varying from minus of n minus 1 by 2 to plus of n minus 1 by 2, that is from minus 3 to plus 3. Since n is equal to 7, n minus 1 is equal to 6. For n equal to 0 to 6, we have to compute HD of n. But here making use of property of symmetry of HD of n, we will compute first HD of 0 to HD of 2, and then equate HD of 6 to HD of 0, HD of 5 to HD of 1, HD of 4 to HD of 2. That is HD of 0 equal to sine of 0.2 into pi into 0 minus 3 into 180 by pi divided by pi into the bracket 0 minus 3, that is equal to 0.2 1009. And this is what now? This is equal to HD of 6. Similarly, we will compute HD of 1, that is equal to 0.1514. You put similarly here. And in HD of n, you go on changing the value of n. To get HD of 1, you have to put n equal to 1. And HD of 1 is 0.1514, which is equal to HD of 5. HD of 2 is equal to 0.1871, that is equal to HD of 4. Next we have to get impulse response H of n. To obtain H of n, multiply HD of n with rectangular window, that is WR of n, where WR of n is equal to 1 for n equal to 0 to 6 and is equal to 0 for other values of n. Therefore, WR of n is equal to 1, 1, 1, 1, 1, 1, 1. Hence, WR of n is equal to 1, 1, 1, 1, 1, 1, 1, and HD of n equal to 0.1009, 0.1514, 0.1871, 0.2, 0.1871, 0.1514 and 0.1009. Multiplying these two, we get H of n equal to WR of n into HD of n equal to same as that of HD of n, because all samples in WR of n are equal to 1. So 0.1009, 0.1514, 0.1871, 0.2, 0.1871, 0.1514 and 0.1009. Next step, we have to find the Z transform of H of n. So right here, taking Z transform of H of n, we get H of Z equal to summation from n equal to 0 to n minus 1 H of n into Z raised to minus n. That is 0.1009 into the bracket 1 plus Z raised to minus 6 plus 0.1514 into the bracket Z raised to minus 1 plus Z raised to minus 5 plus 0.1871 into Z raised to minus 2 plus Z raised to minus 4 plus 0.2 into Z raised to minus 3. So this is the required transfer function of low pass FIR filter of given specifications in the question. I request all of you to realize this filter using linear phase structure and then evaluate its frequency response and verify the results. Dear students, I will stop the class here and continue in next class with designing of FIR filters with the remaining windows. Thank you.